Picture this. You have just finished frying a batch of golden, crispy chicken. The oil in the pan is still clean looking. It is barely discolored. You paid good money for that bottle, and there is at least half of it left. So you let it cool, pour it back into a container, and slide it into the cabinet for next time. Almost every home cook on the planet does exactly this. It feels sensible. It feels thrifty. It feels completely harmless. But here is what nobody tells you. The moment that oil hit a hot pan, a chemical clock started ticking. And every single time you heat it again, that clock speeds up. The oil sitting in your cabinet right now is not the same oil you bought. At the molecular level, it has already begun to change into something quite different. Something that your body was never designed to process. Welcome to Normal Things, Crazy Origins. Today we are uncovering the science of what actually happens inside your cooking oil every time you reuse it, why it matters more than you think, and exactly how to know when that oil has crossed the line from kitchen staple to hidden health hazard. To understand what goes wrong with reused oil, we first have to understand what cooking oil actually is at the molecular level. Because most people think of oil as a simple, stable liquid, something inert, something that just sits there doing the frying. The reality is far more interesting and far more fragile than that. Cooking oil is made up almost entirely of molecules called triglycerides. Picture a triglyceride like a capital letter E. The vertical backbone is a molecule called glycerol. The three horizontal arms extending out from it are long chains of carbon atoms called fatty acids. These fatty acid chains are where all the action happens. Depending on the type of oil, these chains have different lengths and different chemical structures. Some are saturated, meaning every carbon atom in the chain is bonded to as many hydrogen atoms as possible. They are chemically stable, hard to break apart. Others are unsaturated, meaning some carbon atoms have double bonds between them instead, creating slight kinks in the chain. These double bonds are where the oil's vulnerability lives, because double bonds are chemically reactive. They are the open doors through which heat, water, and oxygen can enter and cause damage. Now put that oil into a hot pan. You are typically frying at temperatures between 170 and 190 degrees Celsius. At that heat, three separate chemical processes begin attacking your oil simultaneously, and each one makes the next use more dangerous than the last. The first process is hydrolysis. The word breaks down simply. Hydro means water, lysis means to split apart. Every piece of food you drop into hot oil brings moisture with it. That moisture, meeting extreme heat in the presence of oil, causes a reaction that literally splits the triglyceride molecules apart. The three fatty acid arms break away from the glycerol backbone. These free-floating fatty acids are not inherently dangerous in small quantities, but they are the first sign that your oil's molecular structure is breaking down. They also lower something critically important called the smoke point. The smoke point of an oil is the temperature at which it stops shimmering and starts producing visible smoke. Fresh vegetable oil might have a smoke point of around 230 degrees Celsius, but every time you fry with it and hydrolysis breaks off more free fatty acids, that smoke point drops. By the time you are on your third or fourth reuse, an oil that originally required nearly 230 degrees to smoke might start smoking at 160 degrees, well below your actual frying temperature. And when oil smokes, it is not just an inconvenience. It is a signal that the oil has begun producing harmful compounds and is actively breaking down at an accelerating rate. You have pushed it past its safe operating limit. The second process attacking your oil is oxidation. Every time your oil sits in an open pan or cools and is stored improperly, oxygen from the surrounding air reacts with those vulnerable double bonds in the unsaturated fatty acid chains. This is the same fundamental process that makes butter go rancid, that turns old nuts stale, that causes the distinct unpleasant smell of old cooking oil. Oxidation snaps those double bonds and creates a cascade of new chemical compounds. Some of these are relatively harmless flavor compounds that make older oil taste slightly off, but others are genuinely concerning. One major family of compounds produced by oxidation is aldehydes. Aldehydes are reactive molecules that have been linked in research studies to cellular damage, inflammation, and in long-term high-exposure scenarios, to more serious health concerns. When oil has been oxidized repeatedly through multiple heating and cooling cycles, the aldehyde concentration rises substantially. You can often detect advanced oxidation before you even heat the oil. If your stored oil smells sharp, sour, or reminds you faintly of old paint, oxidation has already done significant work. The third process is polymerization, and this one is visually unmistakable once you know what to look for. As oil is repeatedly heated, Some of the broken fatty acid fragments begin bonding to each other, forming larger and larger molecular chains. The oil becomes thicker, more viscous, stickier. This is exactly the same chemistry that makes varnish harden on a wooden surface. In fact, linseed oil, which is a plant-based oil very similar in structure to cooking oil, is the primary ingredient in traditional wood varnish. When you see old frying oil that has turned dark, almost syrupy, and coats the inside of the pan with a sticky residue that is hard to wash off, you are looking at polymerization in its advanced stages. That oil is no longer just degraded. It is chemically transforming into something the human digestive system has no reliable way to process. Now here is the part that surprises most people, because the question is not simply whether reused oil is bad. The question is how bad, how quickly, and whether it can be managed. The answer is more nuanced than the extreme positions you will often hear. Used cooking oil is not like a light switch that flips from safe to dangerous at a precise moment. It is a gradual, continuous degradation. Think of it like a car's engine oil. Fresh engine oil is clean, clear, and fully functional. After one oil change interval, it is darker and carrying some contaminants, but it is still protecting the engine. Push it 2 or 3 intervals beyond the recommended change, and you are now running an engine on oil that is actively causing more wear than it is preventing. Cooking oil follows the same logic. 1 or 2 additional uses, under the right conditions, does not turn your kitchen into a chemical laboratory. But every additional use compounds the damage, and the conditions under which you store and reuse the oil make an enormous difference to how quickly degradation occurs. The type of oil matters enormously. Oils with a high proportion of saturated fats, like refined coconut oil or ghee, are significantly more stable under heat because saturated fats have no double bonds for oxidation to attack. They degrade much more slowly. Oils with high amounts of monounsaturated fats, like refined peanut oil or high oleic sunflower oil, occupy a practical middle ground. They have enough stability to handle high heat frying and modest reuse. Oils dominated by polyunsaturated fats like standard sunflower oil, corn oil, or flaxseed oil are the most vulnerable. They have many double bonds, which means more doors for oxidation and hydrolysis to enter. These oils degrade fastest and are the worst candidates for reuse. There's also the question of what you fried. Breaded foods shed particles into the oil constantly. These particles sink, sit on the pan bottom, and burn. Burned particles dramatically accelerate all 3 degradation processes. An oil used to fry plain French fries will be in significantly better condition after 1 use than an oil used to fry battered fish, simply because of the additional contaminants the batter introduced. So what does responsible reuse actually look like if you choose to do it? The first step is filtration. After the oil has cooled completely, strain it through a fine mesh sieve or a piece of cheesecloth to remove every burned particle you can see. This single step dramatically slows degradation by removing the compounds that accelerate further breakdown. Second, storage matters far more than most people realize. Oil should be stored in a sealed, airtight container, away from light and heat. Oxygen and light are the primary drivers of oxidation between uses. A dark glass bottle in a cool cupboard, not on the counter next to the stove, is ideal. Third, pay attention to the oil's behavior when you reheat it. If it reaches smoking temperature faster than it used to, if it smells sharp or unpleasant before it even gets hot, if it looks noticeably darker or thicker than when you last used it, those are your signals. The oil has crossed a threshold and should be discarded. As a practical general rule, well-filtered, properly stored oil used for frying similar foods can reasonably be reused 2 to 3 times. Beyond that, the accumulation of aldehydes, free fatty acids, and polymerized compounds becomes difficult to justify from a health standpoint, regardless of how the oil looks or smells. Appearance alone is not a reliable indicator. Oil can look reasonably clear while carrying a significant chemical burden that no amount of straining can remove. So the next time you finish frying and reach for that container to save the leftover oil, you will know exactly what is actually happening inside it. Every use is a countdown. The triglycerides are splitting, the double bonds are breaking open, the molecular chains are growing longer and stranger. The oil is slowly transforming, one fry session at a time, from a simple kitchen ingredient into something your body was never built to handle in large quantities. It is not a reason to panic. It is not a reason to throw out every bottle of oil you have ever touched. It is simply the science, and knowing the science means you can make the choice with open eyes. If you enjoyed this journey into the hidden chemistry of your kitchen, hit that like button, share this video with someone who always pours the oil back in the bottle without a second thought, and subscribe to Normal Things, Crazy Origins for more stories about the extraordinary science hiding inside the most ordinary things in your life. Thanks for watching.